My name is Marcus Munafo, and I'm here to talk to you about research reproducibility as part of the Perform toolkit for early career researchers. I can trace my own interest in reproducibility back to my PhD, although I didn't think of it in those terms then. I was starting out with my first experiment attempting to replicate a finding that looked, from the published literature, like it should be absolutely robust, and I wasn't able to replicate that finding. And it was only because I was fortunate enough to meet an academic who told me that actually that finding was much flakier than the published literature would imply, that I was able to realise that the problem wasn't that I was a bad scientist, but that what I saw in the published literature was not necessarily an accurate reflection of all the work that had been done in the past. Then in my postdoc, I was looking at whether particular genes were associated with response to smoking cessation treatments and reviewing the relevant literatures to identify which genes we should follow up. This was in the days when genotyping was done by hand and was expensive and laborious, so we had to be quite focused. And I began to realise two things. One was that the published literature was not as robust as a casual reading would suggest when you actually combined all of the evidence quantitatively, but also that there were interesting patterns in those literatures. For example, that initial findings were much stronger than subsequent findings, and the evidence, if anything, for these associations tended to tail off over time. And that piqued my interest in what factors might be shaping the behaviour of scientists and shaping what findings make it through to the published literature. The main question is the extent to which science is functioning optimally, if you like. It's important not to be too nihilistic about this. People have described the situation as a reproducibility crisis, but I don't think that's particularly healthy language, because these issues aren't necessarily new issues. People have been talking about studies being too small to give robust findings, for example, for a long time. But what we have seen over the last few years is a growing awareness that some of the ways in which science is working may not be in the best interests of science itself, if you like. The competitive climate for publication and grants, for example, and all of the various pressures that we work within that encourage us to focus on novel, groundbreaking findings at the expense of more confirmatory, solid research that underpins that, if you like. So the question is, to what extent are these problems unique to one particular science, or are something that reflect wider issues across a range of different sciences? And I think that's an ongoing question, an open question. But certainly there is growing awareness that we should at least be looking at these questions and trying to understand the extent to which we are working as effectively and efficiently as we can do, and whether we can improve on the situation. And so in that sense, I think it's better to think of the situation we're in as an opportunity to reflect on the ways in which we work and look to see if we can improve those in any way. So much of the discussion around reproducibility has been in the field of psychology. I don't think that's because psychology has a particular problem when it comes to reproducibility. I guess I would say that as a psychologist. I think, though, that the reason that that is the case is because many of the issues that may contribute to issues of reproducibility are related to human behaviour. In other words, scientists, however well trained they are, however objective they try to be, are also human. And humans are fallible. Humans have various cognitive biases that can shape the way that they interpret their data. For example, people might be excited by results that confirm their prior beliefs and align with those, and therefore less inclined to test those as rigorously as if the results didn't align with what they were hoping to see, for example. Understanding those cognitive biases and understanding the fact that science is a human endeavour is important if we're to understand what we can do to improve the quality of science and the efficiencies of how we work. So when I have these discussions around reproducibility, often it's early career researchers who are particularly conscious of the pressures that they're under. Everyone goes into science enthusiastic about the work that they do, keen to discover new insights into the way that the world works. And as they progress through their PhD and their postdoc, they realise that whilst that may still be their primary motivation, they also need to be publishing and publishing in certain kinds of journals if they're going to have a career in the first place. And that's where the pressures and incentive structures start to play a part, that scientists realise that if they're not publishing in certain kinds of journals, if they're not generating certain kinds of results, novel, eye-catching, groundbreaking results, then they are going to find it more difficult to have a career in the first place. And so it's that pressure which I think can start to shape people's behaviour, usually unconsciously, in ways which may not be to the advantage of science. So of course one of the counterpoints to this sort of argument is that science is self-correcting, and that over time any mistakes that creep into the literature, any findings that turn out not to be robust will be weeded out. And of course that's true in principle. The scientific method has a self-correction mechanism built into it, but it's only true if that self-correction mechanism is deployed. So for example, if we claim a particular finding, and then no one makes any efforts to actually replicate that finding and see whether or not it can be reproduced in other labs using similar methods, for example, then that self-correction mechanism isn't being used. And there is evidence that replication studies, for example, are not valued as much as novel groundbreaking studies, and that when they are published, they're not cited as frequently. So I think the extent to which science is self-correcting and self-correcting as rapidly and as efficiently as it could do is an empirical question. And we have to look at the ways in which we incentivize different kinds of science, the novel groundbreaking findings over the confirmatory replication studies, for example, and ask whether or not the balance is right. And Ottoline Leiser, a plant scientist at Cambridge, has this great quote, which is that it's fine to do groundbreaking work, and we're told all the time as scientists that we need to do groundbreaking work. But why do you break ground? You break ground to build something. And if all you're doing is groundbreaking work and nothing else, then all you end up with is a bunch of holes in the ground. So it's worth thinking about what we mean when we talk about reproducibility and replicability. We're not interested solely in being able to replicate a single finding as many times as we want to. That might be important to ensure that that finding is robust. But what we're really interested in is getting the right answer to the question that we're asking. And it's worth bearing in mind that scientists are not actually directly incentivized to get the right answer. The things that we're rewarded for are for publishing, and particularly publishing in certain kinds of journals, for getting grants, and those are all of the things that we are proximally incentivized to do. There are prizes for getting the right answer, if you like, things like Nobel Prizes, but there aren't many of those. On a day-to-day basis, the things that we're rewarded for are proxies for getting towards the truth, if you like. And so as a result, our behaviour starts to be shaped towards those proxies, towards publication and getting grants, rather than to getting the right answer. And so that's why I say that what might be good for scientists, in other words, what might help them to get papers and grants, might not be good for science itself. So because many of the issues around reproducibility stem from these incentive structures that scientists work within, many of the questions that are being asked are around how those incentive structures and those incentives can be changed to promote behaviours that are better aligned with what's in the interests of science. And those changes will, for the most part, need to come from the top down, from journals, from funders, from institutions. And we are beginning to see initiatives that are attempting to do this. For example, many funders are now requiring applicants to say something about what they will do to ensure the robustness and replicability of their findings, for example. Journals are beginning to introduce reporting checklists to ensure that there is clarity and transparency in the reporting of findings published in their journals, whilst institutions are increasingly signing up to the Declaration on Research Assessment, for example, which says that they won't use inappropriate metrics to judge the quality of individual scientists or individual pieces of work. But if we want to improve the quality of the work that we do as individual scientists or research groups, what can we do ourselves? This is where I think open science comes into play. So open science covers a range of different ways of working that all have at their heart the idea that the greater the degree of transparency, the better able others will be to check the quality of one's work. So we have open access publications, which mean that those publications can be accessed by anybody, but we also have open data, open materials, open code. Pretty much anything that we do can be done in an open way by making sure that our work is available, visible to anyone who cares to look at it. So how does open science improve the quality of the work that we do? Well, there are a couple of examples that illustrate how it might do that. One is open data. So when we know that our data will be open to the general public or to anyone who cares to check it, the implication is that if there's an error in our data, it might be found by someone. Now, of course, that's a good thing. Identifying errors in data and errors in analyses is a good way in which science can self-correct. But knowing that that possibility is there, in our experience, leads people to check their data 4 or 5 times before making them open, whereas previously they may have only checked them 2 or 3 times. So in other words, the potential for someone to find an error in your work just increases the tendency to check everything a couple more times, and that introduces a degree of extra quality control to one's workflow. Similarly, pre-registration of study protocols, making those materials open, allows people to check that what you claimed in your published report, in your journal article, for example, matches what you said you were going to do in the first place. But also, it serves as a check on our own enthusiasm when we see the data in front of us. When we see the data, it might make perfect sense for us to look at a particular subgroup, for example, and it can be easy to fool oneself into thinking that you had always planned to do that because it's so obvious when you see the data in front of you. Then you go back to your protocol and you see that you didn't plan that in the first place. It doesn't mean that you can't do that analysis. There's nothing to stop you doing whatever you want with your data, but it means that you are forced, if you like, to be transparent and clear about what were your pre-planned confirmatory tests, if you like, and what were your exploratory analyses that need to be treated slightly differently because they're exploratory and were unplanned. So it just introduces, again, a degree of clarity and transparency and acts as a check on our own enthusiasm and cognitive biases. I also think it's worth thinking about the extent to which these issues around reproducibility link to the public understanding of science. For the most part, scientists are still well trusted by the general public, but there can be confusion generated when scientists publish conflicting findings over time. For example, that coffee may be good for you one week and bad for you the next week. And the general public, I think, quite rightly, starts to feel like they're getting inconsistent messages from the scientific community. There's also a concern that scientists may be overstating their findings. It's often assumed that any findings that are overblown in the media are the consequence of journalists over-egging the evidence, if you like. But actually there was a nice study in the BMJ a few years ago showing that these examples of hype, if you like, in scientific findings that make it through to the media and the general public can be traced back to the press releases themselves. And those press releases will have been signed off by the scientists. So we are to some extent complicit in this pressure that we feel to ensure that our work is communicated to the general public, and the need to perhaps overstate our findings to make sure that, that those findings do get communicated via the media. So we need to be thinking about how the work that we do, the quality of the work that we do, the robustness of the work that we do, also impacts on how we're perceived by the wider world. So these issues are meant to be provocative, thought-provoking. So here are some questions for you to perhaps think about. One is, to what extent do you think your own cognitive biases might have shaped the way in which you've interpreted your data or conducted your research in the past? Another is what you think you can do as an early career researcher, what scope you have to introduce into your workflow some of these open science practices that we've been talking about. Another is, what are the pressures that you're under and how might those pressures actually shape the work that you do in ways that might not actually be in the best interests of science?